Hello. Okay, good day. So for today we will discuss lesson 2.1, horizontal curves, simple curve. So for this lesson, it is under the course outcome 3, which is recognize the geometry employed in the design and layout of both horizontal and vertical curves. So for the learning outcomes of this lesson is to identify different parts of the horizontal curve and solve simple curve problems. Highway curves are formed by straight sections, which are tangents, since tangent lines are straight lines, of most types of transportation routes, such as highways, railroads, and pipelines, and they are connected by curves in both the horizontal and vertical planes. An exception is a transmission line, where a transmission line is formed by a series of a straight line. They cannot form a curve unless shorter distance between the tower is erected. No? So those are the difference between the curves and the transmission line. So when we say transmission line, it's just formed by straight line. So for example, we have tower here, and tower here. Let's say towers, transmission line, towers. Once they are connected with wires, so they just form a straight line. Unless on highway curves or railroads, we have freedom to design the road. It could be a series of straight line, then a slight curve, then a curve, and another curve. So such as that, no? As an example. So highway and railroad routes are chosen only after a complete and detailed study of all possible location has been completed. That is, it includes planning by the use of aerial imagery, ground surveys, and analysis of existing plans and maps. So there are many considerations in designing of a highway because we need to consider existing structures, topography, what else? So, and so on. There are so many things to be considered. The cost. So that's why there's a need to conduct ground surveys, to to include the existing plans and maps, no, for consideration, and aerial imagery to view the current situation of that area, no, because when we say highway and railroad routes, we need to clear that area because that's the area which we will lay out the road. It should be clear. So, so we denote this as ROW, or road right, RR, right of way. So this area should be cleared so that we can lay out the road, or what kind of road are we putting to, no? So we need to clear that route. So again, the center line of our road consists of series of straight lines interconnected by curves. So curves are also used to change the alignment, direction, or slope of the road. So the horizontal curves are computed after the route has been selected. Once we already selected a specific route, so after the field surveys been conducted and necessary topographic feature have been plotted, so therefore the designer or the engineer can select the best route for this section. So this route might include straight lines or a curve if there's a need to use a curve, no? But in most travel or most design, preferably we need to use, or much better if the road is a straight line, because there's almost no change in direction, no? So in urban work, the curves of streets are designed as integral part of the preliminary and final layouts, which are usually done on a topographic map. So if you can notice, let's say you are going to Tacloban from Baybay, higher elevation area or mountainous area, you can observe that there are so many curves, endless curves, as you may say, no? This is because before they considered a topographic map, no, or contour map. So the designers of road consider the topography of the area um, instead of making a bridge from this point to this point. So they decided to follow the topography. So that's the existing situation of the highway. Okay, so in your opinion, or in our opinion, or my opinion, now why did they chose this road instead of this road? Uh, this road over this road. So because possibly the cost of making this road is greater than this design. So that's why consideration in the designing roads is the cost, aside from the aside from the shortcut. We call this shortcut, right? Because this is just a straight line. So again, if you consider the topography, you need at this section, you need to fill in, as well as this one, you need to fill in that area in order to support your road. So it's somehow like a bridge. So if you're making a bridge, it will cost the contractor much, or the client, let's say the government, right? Okay. So there are two types of highway curves. So for the purpose of this lesson, we will just discuss horizontal curves. But anyway, we will introduce it to you today. So horizontal curves is the first one, which those curves that change the alignment or direction. So as you can see, this one, so from a straight line, then into a curve. So this is the basic geometry of a simple curve. So we will just talk about this later. Horizontal curves are made up of circular and transitional curves. So in circular curves, they have uniform radius. So the other type of curve is the vertical curve. So this curve, which is changing the slope, considering two different kinds of slopes. So we have grade 1 and grade 2. Okay. Anyway, we will just discuss more on this in our next topic. So in horizontal curves, it is used in horizontal planes or in flat to connect two straight tangent sections. So we have here a simple curve, which is we have a straight line. Then we introduce a simple curve to connect the two tangents. And there are two types of horizontal curves. As I said lately, we have these circular, this one. So for the spiral one, spiral is different um, with the circular arcs that we are mentioning. So why? Because spiral sometimes denoted as the transition, no? Transition. Meaning to say, before we before we enter the curve or the circular curve, the spiral helps a smooth transition from straight line to curve, different to simple curve. The transition is at that instant. Once you enter the curve, the change of direction is instant. Whereas in spiral, we have this called transition, meaning to say gradual change of direction. So the principal consideration in the design of a curve is the selection of the length of the radius or the degree of curvature or degree of curve as they mean. So again, the selection is based um, also on the design speed of the highway and the sight distance. So it's not only about the cost, but we need to consider the safety of the travelers, users of the road, and other objects or living things, as we say. Okay, okay. So we have this geometry of a simple circular curve. So again, it is we have the tangents, which are the straight lines, so such as this one. So the subtangent. So if we consider the direction or the increment of stationing is going that way, as shown here, going this way also. So therefore, this tangent is what we call the back tangent, and this tangent is called the forward tangent. Okay. So we have also BC or beginning of curve. Sometimes some reference denote it as BC, meaning to say point of curvature. That's literally. So at this point, so from straight line at this point, this is where you start to change your direction. So that is why this is called the point of curvature. And again, the length of the curve or L is dependent to the central angle and the radius. So 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 this is also equal to delta, which is this one. Diba? The deflection angle of two tangents. So this is equal to this central angle. Take note there are so many references uses delta as your central angle, I as the central angle, or any variables that they want to use. So it's up to them or it's up to you. What is important is you know the parts and the geometry, by the way. Okay, okay. So your L here on for the simple curve, this is only an arc. So meaning to say, or if your central angle is 360, that is your circumference. So okay. So we have also EC or end of curve, which is the alignment changes from circular to tangent. So other references denote it as PT, station PC, and station PT. PT means point of tangency. So meaning to say, from at this point, the curve ends, and now you are going back to a straight line, so which is tangent. So that is why it is called point of tangency. Okay, so now for the simple curve, we have this figure. It's very simple, right? So the radius and radius, such as this one, determines the sharpness of or flatness of the curve. So for the compound curve, um, consists of two simple curves joined together. So this is one simple curve, and this is another simple curve. So if there are some terrain that requires the use of this, so this can be employed. But as much as possible, um, this design should be minimally used, okay, for safety reasons also. But if the terrain cannot permit, no, so therefore we introduce speed limits. So here, as stated lately, for safety reasons, for the reverse curve, it should be avoided. Why? Because at this point, the your direction changes instantly to this direction, which is that before at this point, your direction is going that way. So it would be somehow dangerous. No. So again, it is similar to compound curve. Again, the difference is the connecting radius of this curve is turning or changes its direction in opposite way. Whereas in compound curve, the change of direction or this side of direction is the same. So for a spiral curve, no? So this is somehow the difference between the most of them. So this spiral curve is a curve that has a varying radius. So this design minimizes the passenger discomfort. Meaning to say, at this point, this is where the point where we introduce the spiral, then up to this point. So meaning to say, the radius of this at this instant, the radius is somehow infinity. Meaning to say, at this point, this is still a straight line. But as we move on connecting to this radius or to this curve, circular curve, it slightly changes from infinity to this radius. Meaning to say, from straight line, then slowly changing its direction. So that's spiral curve, which minimize the passenger discomfort. The transition changes gradually. So this design is used on railroads and most modern highways. And also we introduced the super elevation. Super elevation is somehow like this, a banking curve, right? So it's just this one. So when I say super elevation, like this one. So if you look, this is the surface, road surface. So if you look in the cross section, it looks like this. So this is the super elevation. So this is the road. So this is the, for example, the vehicle. Sorry for the drawing. So that's the vehicle. So this super elevation helps the vehicle to change its direction. So physics, right? So banking curve. Uh, Other term for this is banking curve. So just try to search for this one, okay? So now we introduce the degree of curvature. Sometimes we design roads based on these terms. So we have D in degrees. In designing a curve, there are two definitions used for the degree of curvature. First, we have the arc definition, and second, we have the chord definition. So when we say arc, so by arc, write this one. And by chord, we have this one. Okay? So we have this formula now we introduced. So we have the radius is equals to this value, degrees meter over d. So when we say we want to design a road with degree of curvature of um, this angle, now we have this kind of radius. Or by chord definition, so if we want to have this kind of degree of curvature, so we in, introduce this into the equation, then we have now your radius of the simple curve. So you can interchange the equation as much as you want. So it based on the problem and based on the design. Okay. So for this stationing, so we have this example. So as you can see, BC station is 0 plus 196.738. So since we are using metric or SI units, so we will stick to this kind of stationing. So meaning to say 0 plus 196.738 is just equivalent to 196.738 meters, let's say, from the start. So to determine station PI, that is just equals to BC plus your tangent distance. So that is equals to 196.738 plus 45.044. That would be equals to 0 plus 241.782. So that's your station PI. But how can you determine the station of the end of curvature? Do we just simply add um, add this value to your tangent? So no. So how do we determine the stationing of this point? It is just simply, let's say, station EC is just simply equals to station BC plus L, meaning to say the length of the curve. So that is 196.738 plus 89.71, so that would be equals to 0 plus 286.448. So how about, so what 0 means? So a question, let's say you have stationing 2 plus 312.5. So the meaning of this is just simply 2300 to 312.5 parts of your simple curve. So we have point of intersection, which is this one, is where the back and forward tangents intersect. So sometimes the point of intersection is designated as V or vertex. Then next we have the deflection angle or the central angle. So therefore, this deflection angle subtended by two tangents, which is this one, is just equal to this central angle, right? So if you review your geometry, then if you would fully understand why this angle is equals to this angle, because this is perpendicular, right? Okay, it is an angle formed by two radii drawn from the center of the circle, let's say point O, to the PC and PT. So this angle denoted somehow by I or delta or theta or any variable that you want. Okay, so for the radius we have this one, this radius. So the radius of the circle of which the curve is an arc or segment. The radius is always perpendicular to back and forward tangents as shown here. So it is always perpendicular. Then we have the point of curvature, which is this one, or station BC. It is the point on the back tangent where the circular curve begins. So again, BC or PC is a point, and it is computed by station PI minus your subtangent to determine your station PC. Okay? Then we have the point of tangency, which can be found at the end of your curve. So this is the point on the forward tangent where the curve ends, and somehow denoted as EC or end of curve. And it can be determined by this formula. The stationing of PC or PT can be determined by station PC plus the length of the curve. Okay, so that's how you determine the stationing of this point, not from PI to PT. Okay, it must be along with the curve. So we have also point of curve, that is any point along the curve. So it could be here, here, and as long as it is along the curve. Okay, then we have the length of curve, this arc distance. We have the tangent distance or the subtangent. so which can be computed by this formula. And we have the long chord, the straight distance from BC to EC. So we have the C, which is the full chord, BC to EC. We have subchord, which is the distance between PC and first station. So if our stationing is, the regular interval stationing is 20 meters, meaning to say if this stationing is, for example, 0 plus 1 to 1.5. So what is the next stationing? Next full station. So the next full station would be 0 plus 140. Why? Because we are using a 20-meter full stationing or interval, no? So we just simply, what's the next possible full station after 21? So it could be 40 because we have 0, 20, 40, and so on. So therefore, your first subchord is station 0 plus 140.00. Next point along the curve is 0 plus 0, 0 plus 160, and so on until you reach EC. Okay. Then we have the external distance from this point to this point, which is called external second, and this is the formula in computing external distance. We have the middle ordinate, which is the distance from the midpoint of the curve, this one, to the midpoint of the long chord. Okay. So external distance and middle ordinate is collinear. So we have an example. So let's assume that we have the central angle of 8 degrees and 24 minutes, and the station of PI is 64 plus 027.46. So the terrain conditions require the minimum radius permitted by the specifications of, say, 2864.79 meters by arc definition. So we are asked to calculate station PC and station PT. So to compute for station PC, we need to have the station PI. So we need to have station PI minus the tangent distance. So station PI is 64,027.46 minus your tangent distance is just simply the radius times the tangent of the half of your central angle, so which is 8 degrees and 24 minutes over 2. So your station PC is equals to 64,027.46 minus 210.38. So now it would become, your station PC is 63 817.08. So to calculate station PT, so that is station PC plus the arc distance or the length of the curve. So station PC is 63,817.08 plus the arc distance is computed by R, then multiplied by the central angle in, so that is in radians. So that is so that the equation would become 63.7.08 plus 420 meters. So now station PT is equals to 64 plus 237.08. Okay, so for the following example, I will leave this to the students for you to practice.